This is going to be a teardown style video on this Tektronix 432 dual channel 25 megahertz analog oscilloscope. As you can see, it's in really beautiful condition. I got it on eBay, but it was in very nice condition, especially for an eBay scope. All the buttons and switches work perfectly well, which, as anyone who buys test equipment on eBay knows, that's kind of a tall order sometimes. So yeah, no scratches, no blemishes whatsoever on the front panel. It's a really, really nice example. Someone cared for the scope a lot, or they just didn't use it. But yeah, since it's in such nice condition, I really wanted to kind of show it off and document what this scope looks like, kind of for posterity, and because no one else on eBay has really made a long video kind of going through what this scope is. One thing I really like about the scope, in addition to the nice large display that takes up the whole left-hand side, is the fact the scope is fully passively cooled, and we'll get to the internals of the scope in a second. But the cooling on the scope is fully passive. It's fully convective. There's no fan, which means the inside of the scope stays very, very nice and clean, in contrast to a lot of other tech scopes that do have a fan blowing air through them, which is, causes the accumulation of dust and whatnot. But yeah, there's not too much to say about this front panel other than the great display on the left, which is very large. And we have the usual analog oscilloscope controls, your vertical sensitivity selectors, your time base right here, coupling for the triggering, and your selections for coupling and whatnot. Over here, your two BNC inputs. And one thing that is worth noting is that this scope uses a pull-out style power switch. So the intensity switch is the power switch, and you pull it out and push it in to turn the scope on and off. Don't love that. Typically combo switches are not my favorite. They tend to be a little bit unreliable, although this one is not the typical, potentiometer that also has a switch in it like some receivers. As you can see, it actually connects to this convoluted mechanical mechanism that runs a rod back into the power supply back here. So anyways, we'll talk a bit more about the construction of this in a second, but very nice front panel, super well laid out, pretty roomy, not too cramped, and very nice vintage switches with that vintage switch great feel. All right, so on the left-hand side of the scope, as you can see here, we have the CRT. It's inside this metal Tektronix signature colored housing, which is very nice. It protects the CRT, of course, from any damage, but it means you can't see the actual tube itself, except for sticking through a few of the holes right there. You can kind of see the CRT a little bit where the pins connect, and then there's another connection right here through this shroud. But anyways, the CRT, of course, is under here, and I like this inspection sticker that we have, which tells you who assembled, inspected, and tested this CRT and gives the serial number as well. I'm guessing these are the names for just the CRT and not the entire scope. I think more people than this were probably involved in the assembly of the whole scope, and also this sticker is on the CRT with the CRT serial number. But anyways, I hope these people had a nice life after working at the Tektronix factory in the 60s, 70s, whenever this CRT was made. I don't know if I mentioned earlier, but this scope production began in 1970. I'm not sure exactly when it ended, but this scope is a kind of mid serial number, as far as I can tell, based on the service manual and the kind of revisions in the service manual. This scope was made after a bunch of the revisions, so it's not a super earlier serial number scope. Probably made in the mid 70s, if I had to guess. I don't know how long the production run for the scope was, but anyways, CRT on the left, and it goes all the way to the back of the instrument there. So this right here is the horizontal board that handles the triggering and the horizontal sweep. And just some general comments about the quality of construction in this instrument. All the connectors are fully gold plated. Let's see if we can focus here. Yep, all the connectors are gold plated. You can see it especially well with this standalone receptacle right here, pin and receptacle. Yeah, fully gold plated. And there's some really funny, interesting components on these boards. I love these variable gold-plated variable capacitors there. It's a gold-plated tuning slug screw with a gold-plated kind of barrel receptacle at the bottom with a Teflon insulator and that little loop of gold wire which makes the electrical connection to the screw. Very cool. And a lot of the plastic package transistors are socketed, which is nice. There are some socketed ICs on the board. There's two up above as well in there. And what else is there to say? A lot of these kind of dog bone style capacitors. I believe these are all capacitors. I know some of them are capacitors based on reviewing the schematic, but yeah, interesting to see, not super common. And you'll notice that there are no electrolytics on this board. There are some tantalum capacitors, like right here, but all the large value capacitors are tantalums. There are no electrolytics on this board, and I know that because I was looking for electrolytics because I thought that a 16 microfarad coupling capacitor, which is this tantalum right here, I thought that might be responsible for the problem I'm experiencing with the scope, which I'll talk about in a second. But when I found it, I realized it was a tantalum and it measures spot on. So that is not my problem. And overall, very nice quality components on these boards. We do have a few carbon composition resistors, the very end of their kind of usage in this like general purpose way, but not that many. I'm guessing they were selected for circuit positions where the value stability isn't critical, or accuracy is also not critical. We do have these funny series resistors twisted together and mounted off the board for better thermals and to get a higher power rating, I'm assuming. So that's kind of funny, but yeah. Otherwise, not too much to say. We do have the large rotary selector for the horizontal mounted underneath this metal can, so it's nice that's protected. And we have these also large axial, I believe these must be film capacitors because this one is a 0.1 microfarad at 35 volts. Very interesting capacitor. I'm guessing that linearity or something was crucial in this position to use such a large axial film capacitor rather than just one of these, you know, ceramic disc capacitors or something like that. But anyways, interesting circuit board here, and let's move on to just discussing some of these switches over here and the basic problem I was having with this scope. And the reason I opened the scope up in the first place was because it was basically stuck with a high pass filter on the trigger circuitry. Everything worked perfectly well, except the trigger will only activate on signals with a very fast rise time or a very high frequency. So as a result, I thought that there was basically a high pass filter stuck on the trigger circuit. My first hypothesis was that it would be this capacitor, which is a coupling capacitor that is a pretty large value, and if it had gone low in value, dried out, if it was an electrolytic, then that could create a high pass filter. But as I found, that is a tantalum and it is perfectly fine, so that wasn't it. Then I thought it might be the high pass filter switch, which there is a high pass filter trigger mode right there, or I guess it is called low frequency reject, but of course that's a high pass filter. And I did check it with a multimeter, and basically the way the switch works is when it's out, so no high pass on, it should just be shorting. It shouldn't be adding anything to the circuit. When you push it in, it adds in a capacitor and resistor filter, so a high pass CR filter, to the trigger circuitry. I think what was happening was that when the switch was out and there was supposed to be no filter, because the switch is not really working properly, it was kind of still placing that filter in circuit. So we were still getting a high pass filter when there wasn't supposed to be one. And as a result, the trigger wasn't working properly. Now I've cleaned out all the switches and it no longer acts flaky. It no longer shows an open reading, even when the switch is out. Of course, you know, when you take a resistance measurement, it's putting DC through the switches. So I was noticing that sometimes even when all the switches were in their outer position, and there's supposed to be no capacitors in series with the switch circuitry, it was still reading open. So now with all these switches cleaned, when all these switches are out and there's no capacitors supposed to be in series, it does read as a short, which it should, to DC. So anyways, I think that's fixed the issue with the trigger circuitry, but we will find out in a little bit when I reassemble the scope. Oh, and one last thing before we flip the instrument over, just wanted to show you, this is the tunnel diode used in the trigger circuitry in its nice little gold-plated package right there, and of course mounted nicely off the board for reliability. All right, so with the instrument on its side, mounted to the side here is this board, which is the intensity board. And this board's kind of interesting because it has, part of it is at high voltage and part of it is at low voltage. And they've put this kind of plastic cover on the high voltage part, which I think can be removed by sliding it this way so that these larger holes are over these pegs, and then you can lift it off. But yeah, it's got some funny components on it. These high voltage capacitors right here, bridging the high and low voltage parts of the board. But yep, just wanted to show that. And these connectors are mounted at kind of an odd angle, which is funny. I think it's for clearance. I don't think the side of the instrument would actually fit on if these were mounted straight. So they've kind of bent them, and these ones over here are quite bent. So anyways, that's sort of interesting. But yeah, not too much else to say about this. Oh, another funny thing is that this board is mounted straight to these mounting brackets. If you look underneath, you'll see there's no insulators or anything. It's just the board is resting right on top of these brackets. And at first I thought these brackets were metal because they kind of look metal, like a cast aluminum or something. But actually there's some sort of a plastic, and they've put metal threaded inserts into the plastic to be able to screw things into it. But the brackets themselves are plastic so that they can mount flush right onto these circuit boards without shorting anything out. So that's sort of interesting. Just another little detail that, you know, the lengths they went to in constructing this thing. But yep, let's flip this fully over now. All right, so now it's flipped and you can see the bottom of the CRT, including, this is the Z-axis board that we were just looking at. And yeah, there's a few things under here that are interesting and worth pointing out. These right here, Q580 and Q530, are the vertical circuitry output transistors. And they're mounted in this very strange way. So you can see they are kind of pressed onto this, I don't know if it's Teflon or if it's a beryllium ceramic or what it is, but this white insulating washer with holes in the bottom that allow the leads to come through. And then on the top, they're pressed in place by this plastic bracket, and the bracket is actually a contact. So you can see there's a lead that runs to the top of each of these brackets, and there is a metal pin that's pressed onto the housing of the transistor, the can of the transistor, and that actually makes electrical contact with the transistor. So that's one of the contacts. And these, you can tell these are the vertical output transistors because that lead goes to these inductors here, and then that goes to the deflection plates of the CRT. So you can see, yeah, there's this one big inductor mounted right here, and then one smaller one that's kind of just floating in the breeze there for each transistor. And then those go to the deflection plates of the CRT itself. So yeah, very interesting mounting scheme for these output transistors. I'm not sure exactly why they're mounted this way, whether it's for absolute minimum inductance or capacitance, or if it has something to do with thermals. I don't know. These are kind of small transistors to be power transistors. So it's sort of interesting. But anyways, over here you've got some large plastic encapsulated high voltage capacitors, Tektronix branded. There's actually a lot of Tektronix branded capacitors in this thing, but it's kind of interesting. Mounted, of course, this is mounted on standoffs like that. Here we have, of course, the delay line, and it's hardline coax underneath this sort of plastic casing, very nicely packaged. And of course, the purpose of the delay line is that the trigger circuitry has a certain amount of delay, of time it takes from receiving the signal to actually triggering and generating the sweep. And so the vertical circuitry needs to have the same delay as the trigger circuitry, so that when the trigger circuitry activates, the vertical signal that's arriving at the CRT is actually the same vertical signal that triggered the trigger circuitry. So the delay line basically aligns the time delay inherent in the trigger circuitry and adds an equal delay to the vertical circuitry. So you have that length of spiral hardline coax there, which looks very cool. And then over here is just the vertical circuit board. Well, not just the vertical circuit board. It is a very, complex circuit board with a lot of components on it. And you can see it terminates in the vertical output transistors right there that we just talked about. Underneath these cans, you have the rotary selector, switch mechanisms for the vertical sensitivity. And you also have a bunch of compensation adjustable capacitors for the, the response of the vertical circuitry. And yeah, not too much to say about the vertical circuit board that I haven't already said about the trigger board and the horizontal board. Very nice, high quality gold plated circuit board, and really nice components in use on this board as well. Should be very, very reliable as long as it's not, abused too much. So yeah, that's kind of all there is that I have to say about the internal construction of the Tech 432. And I guess the last thing to do is to try to fire it up and show you what it looks like working. All right, so I've got the scope reassembled and triggering right now on a 1 kilohertz sine wave, which means that the issue that I used to be having with the scope is definitely fixed, because it did not used to trigger on any sine wave slower than about 5 megahertz. So obviously a huge improvement. And this is great. This means I can use the scope for audio frequency work, which is mostly what I do. And so it means that definitely I was correct that the issue with the triggering was caused by the low frequency filter, the high pass filter being actuated even when the switch was not depressed. And what it used to do, you can see if I press the switch, it used to just scroll and not trigger, regardless of whether the switch was pressed or not. But now the switch works properly and we can trigger on a slow signal. And I'll just show you a few different waveforms here because it's kind of fun to see. So we have square, triangle, and all these other ramp up and down, sine x over x, etc. I did notice one thing as I was just kind of fooling around with the scope. It's great up to about 100 kilohertz or so. So you watch the vertical, watch the height of the wave. At 100 kilohertz, we're still basically correct. It's supposed to be a 200 millivolt peak-to-peak wave, and I'm at 100 millivolts per division. So you can see it's still about 2 divisions. It's pretty accurate. Our vertical sensitivity gain is pretty accurate at 100 kilohertz. So that's enough really for me in my audio frequency work that I mostly do. However, you will see that if we go up to 1 megahertz, we're starting to lose a little bit of vertical gain. And if I go to 10 megahertz, we lose a lot of our vertical gain. So definitely there's something going on at high frequency. The scope is not doing its advertised bandwidth at all with good vertical gain accuracy. So for me, this doesn't really matter too much because I don't do anything really past 1 megahertz at all. But if I were to work on radios or something, and it would be helpful to see these signals, like see the IF of an FM receiver or something, and even this scope's bandwidth is a little bit low for that, but then I would definitely want to look into what's causing the issues with the vertical gain accuracy at higher frequencies. We're just losing some high frequency response on the scope right now. But I've had enough of messing around with this thing. So I'm definitely just going to be satisfied with, I'm going to be satisfied with my decent performance out to 1 megahertz. and call it a day for now. Maybe a follow-up video looking into the high frequency response. That'll be, of course, much more complex. Gonna have to bust out the manual. I already looked at the manual, but gonna have to look in depth at the frequency calibration, part of the manual, because it is passing a signal, obviously, all the way out to 10, 20 megahertz. My function generator only goes to 10 megahertz, unfortunately. At 20 megahertz, who knows, it might be barely passing any signal. So, and it is a 25 megahertz scope. So, that's something that I might try to look into later on. But for now, satisfied that the trigger circuitry is fixed, and I hope you enjoyed the video.